All right. Well, but before we get to all that exciting stuff, we still have to get through the boring stuff, right? Kind of, a necessary step. Okay. So we were talking about top-down design, and we were in the process of designing the algorithm. So let me just go to YouTube one last time to check where we were for channel mediums. Sorry? Yeah, but I don't want to find out exactly where we were at. Okay, so we were. Okay, let me just pop this up here, make it bigger. Oh, okay. Try again. Nope, doesn't work. Try again, make it play. Maybe it would fix the problem. No, play button is actually somewhere else. I'm not clicking the right place. Okay, click it first, and then maximize. Nope, doesn't want to do it that way. Find it.
Is it your resolution?
Increase the zoom on your computer.
Yeah, just maximize here. Nope, doesn't like it for whatever reason. Okay, so we were pretty much done with the algorithm. We are now at the end of the first algorithm. Okay, I'm just going to read it here because I know that those of you at the back cannot read it. Okay, so the algorithm at this point is saying, while n is greater than 1, do find a prime factor f of n, print f because we want the end user to know what is a factor of the number, and then we have n gets n divided by f, and while. Okay, so that's where we left off last time. And what we'll do today is to say, well, we are kind of done at that level, but we are not really entirely done yet, okay, because we kind of procrastinated. Okay, how do I find a prime factor f of n? Okay, so that's something that we didn't do on Tuesday, and we'll continue to do it today. All right, so I'm using a mouse pad here, to do exactly the same thing. We'll go ahead and do it by hand first. Okay, we'll do a few manual examples, and then we'll try to figure out, okay, is there a pattern to the way we get this problem solved by hand? But I'll also cheat a little bit and use a spreadsheet to help me a little bit here, because I'm going to start with a number that is, well, it's obviously a composite number, and some people look at it and go like, yeah, I know which two prime numbers are the factors of this number, but we'll take a look. Oh, it's complaining about stuff that it wants to open. There we go. All right. Let's take a look at the number 8989. Okay, 8989 is, I want to find a prime factor of this number. Okay, some people look at this number and know instantly, that number has got to be a factor of this number. But I'm not going to, explain it. Okay, so what we'll do is we'll go ahead and try to find a prime factor for this number. And I picked this number because it's not trivial. Okay, you cannot just look at this number and say, oh, the least significant digit is a 2, 4, 6, 8, or a 0, therefore it is divisible by 2. You cannot just add up the digits and it's divisible by 3, because it's not. It doesn't end with a 0 or 5, so it's not divisible by 5. So all those tricks, rules of thumbs, do not work anymore. Okay? Now I picked this particular example because now we have to resort to a structured method to find the first prime factor. Is that making any sense? Now if I pick a number that ends with a 2, 4, 6, 8, or 0, you guys can just say, it's divisible by 2. Why? Because we learned that this is a rule of thumb. This is how we can quickly point out, oh, this number is divisible by 2, that number is divisible by 3, 5, okay? But 7 gets a little harder already. Okay, there's no particular pattern to numbers that are divisible by 7. So let's take a look at this one. Okay, so the way we do it, or the way I'm going to do it, is to use a spreadsheet. And the first column is really just the number itself. The second column is a prime number that I'm trying to see if it is a factor of the first number. Okay, so we'll start with 2. And then most people will say, but Tech, isn't that kind of not so smart to try with 2 because it is obviously not divisible by 2? Well, from a human standpoint, it is. But when you're writing an algorithm, we just want an algorithm that works. We'll make it more efficient later. Okay. How do I know that 2 is not a factor of 8989?
Odd number.
Because it's an odd number, which means something, okay? What happens when I divide 8989 by 2? The quotient is not important to me, the remainder is. The remainder is going to be non-zero, okay? It's a 1 in this case, but if it's non-zero, that means the number is not a factor, okay? And there is a function in all spreadsheets that can do this. It's called mod, which stands for modulus. You give it the dividend, and then you give it the divisor. It will give you the remainder of the division. In this case, the division has a remainder of 1. Okay? Let's go. Say again?
Show it again.
Show it again? Oh, I can just click it and you can see it in the equation bar. It's just called mod, which stands for modulus, which is a its own area of algebra. Okay, modulus arithmetic is its own kind of algebra. Okay, but all it is just remainder. So instead of looking at mod as go like what exactly is that, you can just say remainder. Okay, MOD is remainder. So it's the remainder of a division. Okay, fine. In the next row, I'm going to do exactly the same thing. In fact, this time I can just drag this one down. This one, I'll just say, I refer to the previous item, and we'll just add 1 to it. Okay, so this time I'll try 3 as a potential factor of 8989. And because of the way I constructed the formula, now I can just drag the whole row down and just copy the formula because they will work correctly now. If you look at this particular one, you can see it is the mod or the remainder of B3 divided by C3, which is basically all the numbers on that row. So it's working. Okay, this is a pretty easy way to do it. Okay, if I drag all 3 rows down by 1, then it will try 4 as a factor of 8989. Wow, that is really not so smart, is it? Because we already knew that 2 was not a factor of 8989. 4 cannot possibly be a factor of 8989. But let me ask you another question. Is it possible that this method will misidentify 4 as a factor of 8989? No. So it is not incorrect to check 4. It is just redundant or inefficient to do so. Is that okay? Which is all right for us at this point, because as I said, we just want the algorithm to be correct. It doesn't have to be the most efficient way of doing something. Okay, so we'll just say, yeah, it's not the smartest way to do it, but it's not wrong either. We'll just accept it. All right, next one we'll try 5, 6, 7, and so on. And this goes on and on and on until we get to 89. Because 89 divided by 89 is a remainder of 0. That's the first prime factor of 8989. Are we doing okay so far with the process of finding a prime factor of a number? But we could have done this by just randomly picking some numbers, right? We'll try 2, and then we'll try 23, and then we'll try 41, then back to 31. Is this approach any better than the random approach?
Yes.
The random approach is kind of difficult to track, right? I mean, we have to kind of keep track of which numbers you have tried already. And this approach is pretty easy. Okay, try the next one, try the next one, try the next one. What if the number itself is a prime number? Would it stop ever?
Yeah. So when you get
Exactly. When you get to itself, it must have a remainder of 0. So it will stop at some point. Okay. Okay. So now that we have this as an example of how to do it manually, even though it's not the smartest way to do it, but it is still correct. It will find a prime factor correctly. Let's try to write an algorithm to represent what we just did by hand. Okay. Was that kind of repetitive? Do you guys see any type of repetition on this spreadsheet?
As you go down, you're adding one, and then you're also checking the remainder each time.
Yep.
And you can add an if statement, so if it checks the remainder, if it's 0, you continue to the second condition to find the
Okay.
next.
Okay, so I heard several words that are indicative of this is a repetition. We are dealing with a loop. All right, very good. So when we're dealing with a loop, at this point, I'm not even concerned about is it a pre-checking loop or post-checking loop. I just need to know it is a loop. I'm doing something over and over again. Okay, so just like last time, what I'll do is I'm going to use a non-pseudocode representation and just say there's a loop of some kind. Okay, loop and loop. Are we exiting this loop at some point?
Yes.
We are.
Yeah.
Okay, so let's try to express the condition. Exit when the remainder is 0. Okay, so we'll just go ahead and the remainder is 0. And that's it. Okay, I know it's awfully vague and it doesn't say the remainder of which one divided by which one, but you know what? Capturing something is better than not capturing anything. Okay, so we'll capture this algorithm just the way it is, and it's completely vague, but it's a good first step. Okay, just identifying that the remainder is important, is good. Are we doing okay so far? So in the next step, we want to clarify the remainder of what. Okay, so we'll go ahead and say pretty much the same thing. When the remainder of a given number and a potential factor is 0. Okay, that's a little bit better, right? Because now the algorithm is not just saying remainder, but we also know the remainder of what, okay? Because it tells us several things. One is we are given a number, okay? 89 was our example. And we are also trying some other number, another thing, to see if the other thing is a factor of the number that we are given with. Okay, so we have 2 items. Okay, we have to deal with 2 items in this case. So instead of referring to a given number, a given number, a given number, or a potential factor, a potential factor, a potential factor, it's probably easier to give those names as variables. Okay, so we'll just go ahead and define some variables, just so that we don't have to use a phrase to refer to something in the algorithm. So we'll let n be the number that is given, and find a factor of, okay, because that's what we are trying to do here. And we'll also name f be a potential factor of n. Okay, so now that we have these 2 variables defined, I can go back to the algorithm and make it a little bit more concise, because now we do not need to use the phrase. So we can say when the remainder of n divided by f is 0. Right? Means exactly the same thing, it's just a little bit shorter. Okay. So I'm really going through this step by step fairly slowly. Okay. The next step is, well, can we make this even more concise? The remainder of n divided by f is 0. Well, as it turns out, yes, we can, because we can say n mod f equals to 0. In this case, mod becomes an infix notation. In other words, it is kind of like the normal way that we use divide or multiply. The operator is between the 2 numbers it's supposed to work on. Instead of saying mod open paren n comma f, we say n mod f. But it means exactly the same thing. It's the remainder of n divided by f. Any questions about this step? We are just making it more concise. And by the way, the mod operator exists in most programming languages, if not all. All right. Now this step is actually very important, because in order for me to get out of the loop, n or f or both will need to be changed in the loop, so that eventually n mod f becomes 0. Is that making any sense? Okay, because if the exit condition involves 2 variables, n and f in this case, and we know the algorithm is supposed to exit, that means something has to happen to one, the other, or both of the variables. Do we want to make any changes to n, which is the problem that we're given with? In other words, my boss tells me, give me, a prime factor of 89, 89, and I end up saying, I know 2 is a factor of 16. Am I answering the question? No. Okay, so I cannot change n itself, right? I cannot change the problem to make it simpler. So what else can I change? F. Okay, so we know we can only change f. All right, referring back to the example that we did by hand, which column do you think represents f? C, column C. Okay, column C is representing the potential factor. We tried 2, we tried 3, we tried 4, and so on, but until we tried 89, everything else failed. Okay, very good. So now we go back to our notes here. We're almost done, really. So we say, in each iteration, we are just going to bump up the value of f. Okay, just take it to the next one. Yep.
With like the fact that it has 2 and everything that goes, like to where 2, if 2 didn't work, to get out all even numbers, are you able to like do like if and then
Yeah, you could.
yes, then you just exit the loop and turn
Yeah.
it on 2, but otherwise you just like run.
You could, but it's not really kind of worth the trouble because, we have, that will save you half of the numbers, right? But I have another way that can save you a lot more than just half. So we'll get to that one. What you said will, get you faster, because it's not going to check all the even numbers except for 2 itself. So it's a good optimization, but it does require some additional code in the loop itself, because now you have to differentiate, am I dealing with 2 itself or the numbers that are after 2?
So just removing multiples of numbers that don't work when to kind of make it go faster.
If you really want to make it faster, you can also keep track of prime numbers. So you can test it only with prime numbers. Then you can skip multiples of 3 except for 3 itself, and so on. So there are other ways to optimize this algorithm, but I just want to make something I just want an algorithm that is as simple as it gets at this point, and it works. Okay, so this is okay for now. All right, so we're almost done. Except for one thing. This doesn't tell me what is the first value of f that I should try, because the loop is already saying, oh, we'll just go ahead and increment f by 1. And the exit condition says, I want to try n divided by f, and let's see what is the remainder. In other words, in each case, okay, this is a read operation of the variable f, and so is this one here. Okay, so on both lines, neither is specifying, oh, you know what, f should start with this value. So f remains uninitialized in this case. That's not a good thing. How should I initialize f?
Yes, 1.
Okay, you can. Now
Yes.
those are both correct answers. Okay, f can start with 1 or it can start with 2. It depends on what kind of loop you want to use. Okay, so I'll give you 2 potential solutions here. Okay, one solution is to say we'll go ahead and use a while loop. Okay, if you use a while loop, then f has to be initialized to 2 because the first number you want to try with the division is 2. Okay, so we can say when n mod f blah blah 0, do the following, f gets f plus 1, and while. So now I want to ask you guys, what should I put here?
Less than or greater than.
Less than or greater than, not equal to, greater than, those are all good answers. It all depends on whether n itself can be negative or not. Okay, so typically, if that would be fine. Okay, you can say n mod f is not 0. Do the following, which is the same thing as saying n is not divisible by f. That's all it's saying. Okay? So this is one way to do it. The other way to do it, which I'll use just a dash here to separate because they are both okay, they will both work, is to initialize f to 1 and then use a post-checking loop, which is a repeat until loop, to finish the rest. And in this case, what should I say? N mod f blah 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 0. So what should I put in here?
Equals.
Equals, exactly. Until we've confirmed that we have just found a factor of n, we keep looping around. Okay, so these are both correct implementations of what we had a little bit earlier. They both will initialize f to a certain value, and they both will start with 2 as a potential factor. Which one do you think is better, even though they're both 100% correct?
I like the second one better.
You like the second one better? I like the first one better, okay? Because the first one clearly spells out what is the first value of f that I'll be trying, because it is the initialization is right before I use f, for one thing. And 2, I don't need to rely on the body of the loop to tell me, what is going to happen to f so that it becomes the first value that I'll be using. The second implementation is a little bit different, because when I look at this particular statement, I might think that we will start with a value of 1 for the potential factor, but hold on a second here. The loop is a post-checking loop, so that means I also have to take into consideration what the body of the loop is going to do to f, and in order to determine the actual first value I'll be using when I actually get to the condition. That to me is indirect, and it can lead to problems because we don't necessarily remember to read through the whole thing to get to that point.
I think if I can say back to you what you just said.
Go ahead.
What you're saying is that in the second example, it's unclear from the first statement that you need to step into the code, the loop, in order to realize where what your starting point is.
Exactly.
Okay.
Now, in this case, most people can say, well, yeah, but the loop is so simple, we can clearly look through the whole thing and find out what the first value of the f
In
is.
4 lines, that's one thing, but when you have maybe 16 or 20 lines, it may be different.
Exactly. So that's why personally, if I can implement something either using a pre-checking loop or a post-checking loop, but they're both fairly simple, like 4 lines in this case, I would always go for a pre-checking loop. It's just a personal preference, and I think it's more clear in programming to use a pre-checking loop instead of a post-checking loop. So are there any questions at this point about this code here? Go ahead.
In the code, n is not initialized.
N is given to me, so I don't have to initialize it. In other words, my job is, somebody is going to give me a number, and my job is to find a prime factor of the given number. And this loop will do it. I mean, this algorithm will find a prime factor.
So even though the algorithm doesn't specify that n is equal to 8989, that's given to us beforehand.
That before this algorithm starts, it's actually, as far as this algorithm is concerned, it's in the pre-line, it's a precondition, it is given to me. But f is not, okay? F is what I'm trying to figure out. Any other questions? Okay, if there are no other questions, I'm going to make one observation, okay? The observation is related to our example. It's a very good example, in fact. The observation is, if a number is a composite number, so this does not apply, well, I guess to a certain extent it does apply to prime numbers even. But in any type of number, as long as the product itself is greater than or equal to 1, okay? If it is a product of 2 numbers, one of those 2 numbers has to be less than or equal to the square root of the product. Okay, let me spell it out in a different way. Okay, because in this case, 8989 is less than or equal to the square root of 8989 itself. Okay, let me just spell it out in a different way and see if this is better. Okay, so tag claims. Okay, you guys are getting used to this now, right? I mean, tag claims a lot of things, but then he will say, but don't take my words for it, always question, prove it, right? I mean, I don't believe you, prove it. Okay, tag claims that, okay, for A is greater than 0, B is greater than 0, the following must be true, okay? The following states this. A times A is less than or equal to A times B. or b times b is less than or equal to a times b. There's another way to put this too, okay? This can also be understood as follows. P equals a times b. A is less than or equal to the square root of p, or b is less than or equal to the square root of p. P is product, okay? The product of the numbers a and b. The only requirement is a and b must be greater than 0, both. Okay. Are we doing okay at this point? Okay. So that means if a number is a composite number, one of its factor has to be less than or equal to the square root of that number. Give me any composite number. Especially when the composite number is just the product of two prime numbers.
16. 16.
16? Okay, 16 can be factored in many ways. Okay, can be factored as 1/16, right? 1 and 16 is 1 less than or equal to the square root of 16. It meets that requirement. It can also be understood as 2 times 8 is 2 less than or equal to 4. It can also be expressed as 4 times 4 is 4 less than or equal to 4. Okay, so 16 definitely meets this requirement. 16 being P as the product definitely meets this requirement. Any other number?
49.
49. 49 is 7 times 7 or 1 times 49, right? In the case of 1 times 49 is 1 less than or equal to 7. In the case of 7 times 7 is 7 less than or equal to 7. Okay, so it seems like this is a universal truth. Okay, seems like it's a universal truth that if you pick any number a and b that are non-negative or positive, then at least one of them will have to be less than or equal to the square root of the product of these two numbers. Is that okay? You guys getting a general feel of what I'm trying to claim here? Okay, why is that important?
Because it means you don't have to go higher than the square root of 89.
To confirm a number is prime. Ah, so maybe that is really useful, because if I use this method here, okay, so let's pick a different number. That's why I use a spreadsheet, because I can just switch it around real quick. If I pick a number like 101, which is a prime number, what this is saying is I can stop here. Instead of going all the way to 101 and say 101 divided by 101 has a remainder of 0, and therefore 101 is its own prime factor, I can stop right here and say, hey, you know what? 101 is a prime number, and therefore it is its own prime factor. I don't have to test 12, 13, 14, and so on. That is the implication of my claim. Because if what I claim is true, that means if it had any prime numbers other than itself as a factor, I would have found it by the time I hit 11. Yep.
I'm sorry, could you go over that last string again? How and why did you stop at 11?
How can I stop at 11?
How and why?
Because if it has a factor other than itself and 1, either that factor or the other side of the factor has to be less than or equal to the square root of the number. In this case, the number is 101, so the square root is 10 point something. So by the time I try 11, I would have covered, any factor that it has if it had one. But in this case, because 101 is a prime number, it doesn't have a factor other than itself and 1, and that's why I could not find anything, up to 11. But because of that, I can now confirm that 101 is a prime number. I don't have to test any further.
So what about like 37?
37? Well, let's try 37. Okay, so if you change the number to 37, I can stop at 7. I can stop here when I confirm that 7 is not a factor of 37. I can stop. Because if 37 had a factor, if it is a composite number, which means it has
You
a
would have found it by the time you hit
7.
square root of 37,
Yes.
which is a little
6
less
point
than
something.
7, right?
Yeah, it's between 6 and 7. So by the time I get to 7, I know for sure that I would have covered it. Yep.
What happens when you use a number that isn't prime?
That isn't prime?
Yeah.
Okay, but let's give me one that's tricky. Let's try 143, which is 11 times 13. Okay. 143. And what is the square root of 143?
Slightly less than 12.
It's between 11 and 12, right? And guess what? By the time I got to 11, I found it. Okay, now remember what I'm doing here is I'm throwing darts. Okay, and so far the darts have always hit a green area. In other words, they all work, right? Are there any red dots that I have not hit with a dart yet? I don't know. I cannot know for sure. If I just keep throwing darts, I can be just so lucky that I keep throwing darts at the green parts of the circle, and all the red dots that I cannot see, I have not hit yet. So this is not a proof that we can actually rely on this method to make our algorithm a lot more efficient than before. Because in other words, if I have a number that is really huge, let's say it's 6, let's make it 9 million something. Okay, so I have a number that is 9 million something, and I want to see whether it's a prime number or not. I only have to go up to about 3,000 something, and then I can say, you know what? If I cannot find a factor up to 3,000 something, which is the square root of 9 million something, I can say, hey, you know what? That number that is really huge is a prime number. I don't have to go all the way to 9 million something to confirm it. That is a huge saving, even compared to not testing even numbers and numbers that are divisible by 3, by 5, and so on. It is still a huge improvement. Okay? So I really want to use that optimization, but I cannot until I can prove that is true for all numbers. Instead of throwing darts, I'm going to use a proof. Are we still doing okay so far? Okay, so this is what we're going to do, is to prove that we can actually use this particular theorem. Yep.
I have a question. Do you say compound number or composite number? Because I don't know what the term was. I'm not a math
I
major.
do not know either. Let's see. Composite?
I'm pretty sure.
Product of two numbers. Is it composite? Yeah, looks that way. Every composite number is a positive integer that has at least one positive divisor. There you go. So it is a composite number. Sometimes I remember things wrong, like DNS. I always remember in an incorrect way. It's So it's good to look at that. And other professors will say, but Wikipedia cannot be trusted. It maybe this is written by TAC, and therefore it is wrong and consistent exactly the same way, right? I mean, I would imagine that if I wrote something wrong in Wikipedia, someone would have flagged it already and corrected it and banned me from doing any further authoring at that point. Do you guys know that you can actually track how a wiki document has changed over time?
Yeah.
Okay, that's a really useful feature because you can actually check and see whether other people have gone through it and made corrections and stuff like that. For anything that's political, religious, and stuff like that, that can be very subjective, and I would not use Wikipedia as the primary source of information. But for science, math, computing stuff, I would say Wikipedia is probably accurate, if not explaining things in a good way, in a very easy to understand way. It's at least accurate. All right.
More accurate than encyclopedia.
It is,
Yeah.
because it's basically a good example of crowdsourcing. Yep.
Roll sheet.
Roll sheet. Thank you.
I use it for my chemistry classes all the time because there'll be a concept we go over that's too hard to understand.
Mm-hmm.
And Wikipedia says it in layman's terms, so.
Maybe it depends on who's editing and writing that page. But it can improve it, right? I mean, everybody can help improve, what is on Wikipedia. Right. So let's go back to our example here, and then we'll say, can we prove tag is right? Okay. Because that's what I'm claiming. Okay. This is what I'm claiming. Let me just re-point out what I'm claiming here. A is greater than 0. B is greater than 0. Then the product, has to relate. Okay. Okay, this is what I'm claiming. What I'm claiming is, give me a number greater than 0, A, give me another number B greater than 0, and define P as the product of A times B. Then it follows, okay, it implies that A is less than or equal to the square root of P, or B is less than or equal to the square root of P. That's what I'm claiming, okay? So what I want to do is to prove that I'm right. But you know what? To prove that I'm right, I'm going to use a kind of tricky way of proving it, which is called proof by contradiction. Now, proof by contradiction is kind of interesting because it says, let's see what happens when if tag was wrong. Okay, let's see what it will lead to if this particular claim is actually wrong. That's what proof by contradiction starts with. Okay. So we'll say, let's see what happens if tag's claim was wrong. Okay? In this case, wrong means false. Okay, this particular implication part is wrong. Okay. So if I was wrong, then somebody can find a counterexample, right? To say, hey, tag, I just found this number, these two numbers here, where this theorem is not true, right? So we'll go ahead and say, let's say somebody found a counterexample. So that's what we'll do here. Okay. Let's assume someone found a counterexample to prove tag wrong. Okay. What does that imply? I don't need you guys to actually find a concrete counterexample. It just simply means someone can find an A greater than 0, a B greater than 0, define P to be the product of A times B, and yet neither A nor B is less than or equal to the square root of P. Isn't that what it means when I'm wrong in this case? Okay, all right. Okay, so that means someone can find A and B, define P such that. Okay, there we go. A is greater than 0, B is greater than 0, P is still defined to be A times B, and yet A is greater than or equal to square root of B, and B is greater than or equal to the square root of B. In fact, nope, I have to use greater than because that's the negation of less than or equal to. Is that part okay? Does everybody understand, this is what it means when I can find a counterexample? Because my theorem states that at least one of A and B has to be less than or equal to the square root of B. So to find a counterexample means A and B both have to be greater than the square root of P, not B. Sorry, I made a mistake here. It's P, which is the product, and this is P, which is the product. Okay. Is that okay so far? Yep.
Why, if you're finding the contradiction, does it have to be and not or?
Because it's the negation. It has to do with the negation of a or can also be expressed, as a conjunction of the negation of the individual parts. Okay, so maybe we should go there first. Okay, that's a good question. I forgot to mention that first. Okay, so what he's saying is, okay, can we? I shouldn't use A and B, so I'll use X and Y in this case. So the negation of X and Y, is that really saying the same thing as not X or not Y?
No.
Okay, but that's a question. Okay, so it is not the case that X and Y is true Is it really saying the same thing as not x or not y? Well, we can test it, right? I mean, this is Boolean algebra, and we can always test something like this. Okay, so we'll go ahead and test whether this is really the case or not by enumerating all possible cases. Remember this technique? Okay, we're going to use it again. So we have true, false, oops. Keyboard control. All right. If x is true, y is true, what is x and y? X and y is true, right? Because true and true is true. What is the negation of true? False. Good. And the next one has one of x and y is false already. The conjunction has to be false. But the negation of false is true. And I can apply the same argument here. It's just, flipping the two sides. If both sides of a conjunction is false, obviously the conjunction has to be false, which means the negation of that has to be true. Okay, let's try the other column. X is true, not x is false. Y is true, not y is false. False or false is false. Good. And over here we have x is true, not x is false. Y is false, not false is true. So we have false or true, which is true. Okay. And over here we have just the opposite of that. We have x being false, not false is true. We have y being true, not true is false. So we have true or false in this case. Are you guys following me? Okay. You don't have to follow the exact mechanical part of it, because you can always verify the mechanical side, just by doing it by hand, slowly. But this is the general approach. Okay. So in this case, we have x being false, y being false. The negation of x is true. The negation of y is true. True or true is true. You know what? I think I can see two columns being the same. Which two columns? The two columns corresponding to the expressions. So what this means is I can now say, whenever I see something like this, I can re-express it like this, and they are truly equivalent. It is not implied. It's not implied by. It is actually is equivalent to, because when one is true, the other one has to be true. When one is false, the other one has to be false. And that's why it is equivalent. Am I doing okay so far? Okay, so because of that, I can transform this to something like this, because this is also true the other way. Okay, if you not x or y is actually the same thing as not x and not y. That actually works too. I'm not going to go through the proof here, but you guys can create your own truth table to prove that the other claim is also true. Okay. All right. But that was a good question. Thank you, because I kind of missed that step. Okay. So now that we know this is what a counterexample would look like, let's see where the counterexample will lead us just by using algebra. Okay, algebra steps that we already know. Okay. All right. Let's go here and say, well, since a is greater than 0 and p is greater than 0, what happens when I take the square of both sides in this case? Would the inequality still hold? A is greater than 0, in fact, they have to be greater than 1. Okay, so assuming a is greater than 1, greater than or equal to 1, b is greater than or equal to 1. If I square both sides, do you think this relationship would hold?
Yes, should.
It should, right? Okay, just from algebra, we know that it should hold. Okay. So that means, a times a is greater than, just p, because the square root of p times the square root of p is p. Is that making any sense? That by itself is not a big deal. And we can do the same thing over here, right? That by itself is also not a big deal. What if I multiply a times a to b times b? Okay, a times b times b should be greater than p times p, because all of these numbers are greater than or equal to 1. So if you continue to stack them up, the relationship should transfer. Okay? I think we have a little problem here, because I can use normal algebra just using the commutative property I can now say, hey, I can just exchange the order a little bit here. But by definition, what is A times B? So now we have P times P being greater than P times P. That's a contradiction. That is a contradiction because the P times P cannot be greater than P times P. So, okay, wait, hold on. Just take a step back here. So this is saying that if I was wrong, then we'll get to a counterexample, which cannot be. So what do you think is the conclusion?
The fact that someone, or the assumption that someone found a counterexample.
Right. Exactly. So that means I have to be
Tax claims, right?
Tax claim has to be right. Okay. Because contradiction is not good. Okay. For those of you who want to understand how bad contradictions can be as a result, you have to watch the movie Dogma. Some people might get slightly offended or severely offended by that movie, but the movie does evolve around contradiction and how that can be a really, really bad thing. And not to mention it has Ben Affleck too. So
And Alan Rickman.
yeah.
There's way more.
Yes. And also, what is the comedian who played the Archbishop?
Oh God.
Okay, now I have to
Google
look
it.
it up. Now I have to look it up. Dogma, the movie.
George Carlin, was it?
Yes.
George Carlin, that's it. Yeah. I think this rating is really way below what I think it should be.
5 stars.
Why?
If you ask me, it should be way up there. Yeah. Okay, so the movie is Dogma, and George Carlin, was the Archbishop in the movie, and that all by itself should tell you something about the movie.
He's a genius.
Can you go back to the screen real quick? I'm still writing some notes.
Okay.
Oh, yeah, James Bobber.
Yeah.
Yep. All right. So now I have just concluded the proof, right? I mean, because I have proved that no counterexample can exist. What does that mean in the analogy of the green circle and red dots?
No red dots.
There are no red dots. Okay? The whole circle has to be green. Because the assumption that even one red dot exists causes a contradiction. Okay. But that's really the end of the proof. I mean, that's the proof that there cannot be any. My original claim is correct. Now, because my original claim is correct, now I can confidently change the algorithm to stop when f is larger than or equal to the square root of n. And therefore, I can now optimize the algorithm without even having to worry about even numbers and numbers that are divisible by 3 and so on and so forth. And yet the saving is phenomenal when n is a large number, because I'm only doing up to the square root of that number. Not even having or 1/3 of the number is the square root of the number. Okay. Are there any questions at this point about the theorem proving part itself? Yep.
So when you did that step where you just squared both sides, is that what I'm trying to figure out is how would you know to just do that? Are you trying to isolate whatever P, like any with a different problem?
I'm trying to get to a contradiction, so that's
But how would you just know to just square both sides like that?
that's really hard to explain. It's just subconsciously my mind would kind of probe different ways of doing things, and then one way just kind of, oh, okay, I can come to this conclusion. I know what I'm looking for. I just don't know how to walk the path or which path to walk to find the destination.
So it's kind of just a matter of experience, I guess.
Experience and actually spending time, just analyzing the problem. But it always has to go back to the definition or the assumptions. In other words, you have to make use of the first part here. Okay? It always has to go back to there. So you have to kind of look at that and go, how do I make use of the assumptions in order to arrive to a contradiction? There was another hand. Yep.
When you're using the commutative property, that was where you used P equals A times B. in order
Exactly.
to
That's
figure
making
this
use
out.
of the definition that P is the product of A and B. Exactly. Yep. And proof by contradiction is a very powerful technique for proving something. Okay, instead of going forward to prove something, you're actually going in the opposite direction and say, well, let's say I'm wrong, and then we'll see what happens. Okay. If you enjoy this kind of thing, proving theorems and stuff like that, you will like CISP 440, which is going to be one of the last classes that you will be taking in the computer science transfer degree.
Which class is that?
It's called discrete math, but it really is just math for computer science. It's not calculus, it's not linear algebra. This one is truly just related to computer science itself. It's called discrete math. Or called discrete structure. I think the course title is discrete structure, but it's actually just math. All right. All right. So knowing this, okay, this is all cool. So we can now go back to this algorithm and say, how can we improve this algorithm based on what we have just observed? All right. So I know we can get out of the loop earlier now, right? Because that's the whole point. Is so that we can get out of the loop earlier. So I'm going to give you something like this, and we'll go fill in the blanks. Because I know we have to change the condition so that we can get out early, right? So the first question is, what goes to the question mark? Am I going to use and, or am I going to use or if I want to get out of the loop earlier? Or. Now, what is the effect of or? Does the effect of or increase the chances of being true, or does it decrease the chances of being true?
Increases it.
It increases. And when the condition is true, we stay in the loop. Maybe that's not what we want to do. It's conjunction. Okay? Because in the conjunction, if one side is false, the whole thing is false, and then we get out of the loop. So that's why it is actually conjunction that we want here. We want to specify another condition that also has to be true in order for us to stay in the loop.
Oh, just stay.
Yeah, because the condition on a while line specifies when do you stay in the loop. And we want that to turn false earlier if we want to optimize the algorithm. Okay, so the first question is now answered. Let's see what we should do in here. What is the other condition that also has to be true for me to stay in the loop? Okay? And it relates to the theorem that I just proved. Go ahead.
F is
Less than or equal to.
the square root of n.
Okay, that's one way to express it. So we'll say f is less than or equal to the square root of n. Okay, now I can simplify this right away and take out the equal to. The reason why I can take out the equal to is if f is exactly the square root of n, the first one will fail anyway. Right? Because if f, which is an integer, is a factor of n, that means f divided by n divided by f is a remainder of 0, which means the first condition is going to be false. I don't need to bother to check the second condition. Does that make any sense? So that's why I can take out the equal to right away, and then the rest, this works too. The other thing I can also do to express exactly the same logic, but in a slightly different way, is to say f times f is less than n, because basically I'm just squaring both sides to get to the same expression. And this is truly equivalent to the other one, because we know f is at least is non-negative. So it's truly equivalent to the other one. But why would we do something like this? Turning a square root operation on n to a square operation of f.
You're inverting the logic.
Sorry?
So you're inverting the logic.
It's the same logic. It's the same logic. Algebraic, speaking, is really the same thing. It has the same meaning. Could it be?
Would it be because if you were doing square root, you'd have to call some other type of function?
Exactly. Yep. Go ahead.
I was going to say that when you change it to f, so you're going to be evaluating f.
Okay. Let me.
That's what I was going to get to.
Okay. Taking the square of something or multiplication with integers is far less expensive compared to the square root of something. In other words, we can calculate the square of two integers a lot faster than calculating the square root of a number. And that's why I would just change the form a little bit and take advantage of the efficiency like that. Okay. Now, if we're working with sequential numbers, like f can only increment by 1, I can get rid of multiplication altogether. I can actually get to the square of the next number without using multiplication at all. What? I can calculate a square without using multiplication and only rely on addition as long as the numbers are sequential. In other words, if you tell me I can give you, okay, if you tell me n has a square of, say q, okay, I can get to the square of n plus 1 only using addition operations. Is that really possible? Okay, just think back to middle school when you first learned about the quadratic equations. Okay.
Don't you just add, like if you're doing 6 times 6, it would be 36, then the next one
Yeah, but that would be
6 plus 7.
Yeah, but that would be pretty slow too. What I'm saying is, if you give me y equals to x squared, I can get to x plus 1 squared without using multiplication. Okay, so given this, I can find this number or the value of x plus 1 squared without using multiplication. Well, spell it out, okay? X plus 1 squared is x plus 1 times x plus 1. Using the distributive property, we have, x squared plus 2x plus 1. But let's do multiplication here. Fine. There's no multiplication now.
X squared.
Yeah, but that's y. You told me what y was. So now I can boil this down to 3 additions and be able to calculate x plus 1 squared. Is that making any sense? Now, many people look at this and go like, why do you bother? I mean, yeah, it's tricky and it shows that you know your algebra, your middle school algebra. So it's nothing to show off, right? I mean, but why do you want to do something like this?
It makes it more efficient.
It makes it far more efficient when you have a computer, when you have a processor architecture that doesn't even have hardware multiplication. Okay? What kind of processor cannot even do multiplication in hardware and can only support basic arithmetic like addition and subtraction? Well, the 30-cent type of processors fall into that category. Okay, this is one of the reasons why the UC Davis micro mouse robots can use a fairly weak 8-bit processor and be able to handle a lot of complicated stuff that many other schools have given up completely. It's because of this little optimization, it suddenly makes certain things possible because it's not taking up all the processing resources just to calculate the square. Okay, so sometimes this stuff is important. Okay, how do you get rid of taking the square root of something? We end up with multiplication. How do we even get rid of multiplication if the number is always just incrementing? Are we always just incrementing a number here, the number that's being squared? Yeah, because f starts with 2, and then 3, and then 4, and so on. So the square of f can also be tracked accordingly. Now, I'm not going to throw that into the algorithm here. I'm just saying that sometimes optimization like this can make or break a product. Because in certain products, you just don't have the processing power to do a multiplication. It can do it. It's just that if you do a multiplication, you kill the application because it won't have enough time to do what else the other stuff it's supposed to do.
And is that why it's easier to do f times f instead of the square root of n?
Exactly. Yep. That's the first step. That's the first step to eliminate the use of floating point numbers, because the square root is what we call a floating point number calculation. And on processors that can only deal with integers, that's a very expensive operation. It takes a lot of time. But even the square or multiplication is still expensive. So when I reduce it to just 3 additions, that's also a phenomenal saving in terms of execution time. Okay. But I just want to kind of let you guys know, how math plays an important role in programming, because there's no telling when basic math comes in handy, just because you can reduce the operation to something that is far more efficient. Okay. Are there any questions at this point? No questions? Okay, we'll just go ahead and move forward a little bit here, because the algorithm is not done. The optimization is done, but we're not quite done yet. Because now, when the loop exits, f doesn't have to be a factor of n. Okay, because we are just halfway through, we just confirm that n is a prime number. But you know what? At that point, f is not a factor of n. So we need one little conditional statement here to make some adjustments. So what we'll do is we'll say, if blah, 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 then we confirm that n is a prime number, and therefore f is n, because if n is a prime number, its only prime factor is itself. So the question is, how do I confirm that? How do I confirm that n is a prime number? It has to do with the square thing that we did earlier. You just have to figure out what comparison operator you have to use in that case. So how do we confirm, when we get out of the loop from the while loop here, how do we confirm that n is a prime number, and therefore f should be n, because it is its own prime factor? Okay, so let's try it. So we know that it has to do with f times f on one side, n on the other side, and there's a relational operator here. So the question is, what are we going to do? Well, let's see here. This doesn't work, does it? Because if this condition was true, we should still be staying in the loop. Okay, that doesn't work. What about this condition here? If f times f is exactly n, doesn't that tell you that f is a factor of n? Okay, that doesn't work either. So, but by the process of elimination, we know this one has to be the right answer. But it does make sense too. It does make sense because what it's saying is we kept trying potential factors until we get to the point where f times f is greater than n. And yet we still cannot find a factor. But according to the theorem that I just proved earlier, if there was one, I would have found it already. The fact that I could not find one up to this point means n is a prime number. And because it's a prime number, and I'm supposed to find f, which is a prime factor of n, I have to return the correct number. So I have to update f to be the same as n, because n is a prime number in that case. Is that okay so far? Okay. So I'm not sure whether I'm explaining the process of programming, well or not, because that's something that you guys have to do in the next class in Cisp 360. Okay, that's the class where you actually have to write the algorithm and not just trace the ones that your professor is giving. Okay, so I'm trying to illustrate the process of programming, when I'm giving you examples like this. So we'll do this, as much as we can. Every time I need an algorithm to solve a problem, I'll try to describe the process of how to synthesize, how to construct the algorithm itself. If you guys have any questions about that process, or if you have a better idea of doing something, let me know, and then we'll turn it into a discussion. Right? And I'll see you guys next week. Have a nice weekend. No homework at this point. We'll give you one next week. Thank you.
Are super easy. 2 more.